Hi there, chemistry team. Good morning again. You ready for video number 8 in our titration series here? So we got buffers down. We got the common ion effect down. We've talked briefly about buffers, kind of what titrations, what titration curves look like in general. But now we're going to look at specific ones. What's the specific acid? What's the specific base? We looked at indicators, so now we know how to choose an appropriate indicator. Once we get that titration curve, just even if it's this basic, doesn't have to be a beautiful plot, just a basic plot, get a few points on there, and then we can kind of draw a rough sketch of a titration curve, and based on that high rise there, right around that equivalence point, we can find that range, we can find an indicator whose 2 pH unit change falls within that steep rise. We're good to go on that one, preferably, again, colorless to colored. So I forgot to erase. My kids get to my board every night. So this is chemistry from a 9-year-old boy's perspective and a 10-year-old girl's perspective. I get little things every day. And words of wisdom from a 10-year-old girl. Hi, Dad. Remember, relax. That's good information for you guys if you want to live a longer life. Just relax, man. Although I may not be the best person to talk to you about that, but make sure you just enjoy the journey, my friends. So I need to pause this and erase this board so we can do this next video. We're going to look specifically at the easiest titration today, and typically what you do in introductory chemistry or first semester general chemistry. A strong acid titrated by a strong base, or vice versa, either way, but usually we have the acid in the flask and the strong base in the burette, and that is your titrant. Let's go ahead and do that one. For strong acid, strong base titrations, and again, if you start with a strong acid and titrate with a strong base, you're going to start at a lower pH, right, and end up at a higher pH. If you flip that and put the strong base in the flask and the strong acid as the titrant in the burette, you're going to start at a high pH and end at a lower pH. So it's just mirror image of each other. But typically, we put the acid in the flask and the base in the burette. So if we are doing that, and again, remember your strong acids, HCl, HBr, HNO3, blah, blah, blah. Commonly, it's hydrochloric acid in lab, but we could pick any of them. And we're doing monoprotic acids at this point, no polyprotic ones. We're going to do those in a later video. Strong base, typically sodium hydroxide. You could use potassium hydroxide or any other one, but I mean, I don't think I've used, in all the decades I've been teaching, I've never seen anybody use anything other than sodium hydroxide, right? So just plan on that. But theoretically, we can put whatever we want as long as it's a strong base. Monoprotic bases is what we're doing. So overview, 5 main points. Now, obviously, on an exam, I can't ask you all of these. We don't have time. But on homework, or if you're trying to put a basic titration curve together, you want to get 5 basic things done. 4 of them are, ideally, the more the better. The more data points you have, the better the graph's looking. But we just have limited time. All right? Very first thing I like to do, this is, depends on who your professor is. I like to look at the volume and concentration of the acid I'm titrating, which will be provided for you. Obviously, in lab, you probably wouldn't know the concentration you're solving for. So this is a little bit different. We're going to try to put together a titration curve. So we need to know the volume and the concentration of the acid that's in the flask and the concentration of the strong base in the burette. All right? We don't need to know the volume because we're going to be finding out what volumes we need at certain points along the titration curve. Very first thing I like to do, don't necessarily have to go. You can go in any order you want, really. The order is irrelevant on this. But I like to find where is my equivalence point. What volume of that strong base titrant is required to completely neutralize the volume and concentration of acid that I was provided in that flask. So that gives me on my x-axis. I start at 0 milliliters, I go to whatever, 50 or whatever. It'll tell me, is it 25 milliliters where it's the equivalence point, or 27, or 15, or 35? I like to know where that is. That's my breaking point in the middle, and anything before that's the pre-equivalence point. Anything after that's the post-equivalence point. I like to know that value, so I gotta know where I'm at. Otherwise, I feel like I'm, throwing darts with my eyes closed. I don't know what my target is. So once I've and that's just simple stoichiometry, right? You take the volume and the concentration of the acid, figure out the millimoles, 1-to-1 millimole ratio if they're all monoprotic, yay! And then use the concentration of the base to figure out the volume of the base solution required. Once I have that, I'm going to calculate the initial pH. Haven't added any of the titrant yet. So I will just have a strong acid. Strong acids are easy. No ice tables needed. They ionize 100%. Hydronium ion is the same as the original acid concentration. Negative log of that, you got the pH. Easy peasy. Then I like to pick somewhere in the pre-equivalence region, right? So maybe you added anywhere from 1 drop of base to anything up before the volume at the equivalence point. If I can only pick one point, I like to pick it within a milliliter or so of the equivalence point. I like to butt up because there's not much change before the equivalence point, and then boom, skyrockets. So I like to butt up just against the equivalence point there and see how that curve is going into the equivalence point rise. So pick some volume in there. Ideally, if we had time, we'd do like 5 data points in there. But if you only got one, pick within maybe a milliliter of that equivalence point. This is all based on neutralization stoichiometry. Right? I've got acid, I've got base. Right? I've got a set amount of acid to start with. I'm adding less base because it's pre-equivalence, hasn't neutralized yet. So all the base will be neutralized. There'll be a little bit of acid left over. Right? So we need to figure what that is. So find out the millimoles of base you added, subtract that from the millimoles of acid you're starting with. That'll be the leftover millimoles of acid. Divide that by the total volume because we've diluted it. We've added the 2 volumes. So take the volume of the base, volume acid, add them together, and divide your millimoles of leftover acid by that. You'll have the concentration, and that's a strong acid, so 100% ionization. Piece of cake. Not much different than this one. You just have to do that extra neutralization stoichiometry step. So brush up on neutralization stoichiometry if you need to. After I've done that, I'm going to figure out what my pH is at the equivalence point. For strong acid, strong base, they're gone. The original acid base are gone. You only have the products, which is the salt and water. The salt of a strong acid, strong base, we have to look at. Those ions are both neutral. So only water contributes to the hydronium ion from autoionization. So the pH is always 7. Yeah! Don't even have to calculate anything. It's really nice. And then I'll get one post-equivalence region after the volume, right, after the equivalence point. And again, you could pick any point there. I usually like to pick one within about a milliliter of that. If I had time, I'd pick one there and maybe one 15, 20 milliliters down the road to see how that S-curve continues. So again, neutralization. This is the same as the pre-equivalence. It's just flipped. All the acid is going to be gone now, and you're going to have some leftover strong base. Right? Subtract the millimoles of each, figure out how many millimoles of leftover base you have, divide by the total volume. Boom, you can get your pOH, subtract that from 14 to get pH, and you're set. I've been talking a lot. Let's do an example. All right, gang, here's our first problem. So we've got the titration of 15.50 milliliters of a 0.241 molar hydrobromic acid solution, recognizing HBr as a strong acid, with 0.309 molar potassium hydroxide solution, potassium hydroxide being a strong base, so we recognize that. So part A, let's figure out what's the titrant volume, which is the base. So what volume of potassium hydroxide solution is required to completely neutralize that amount of HBr? So go ahead and do that for me. Pause it, take the volume and the concentration. And again, remember, molarity is moles of solute per liter solution or millimoles of solute per milliliter solution. Since we're starting with milliliters, if you do millimoles per milliliter, you can just work everything in millimoles and milliliters and avoid all those 1,000 to 1 milliliter to liter conversions. Really saves a lot of time. So go ahead and do that stoichiometry and figure out the volume of KOH necessary for me. Looks like we're going to be limited to 3 significant digits there. How's your math looking, my friends? Well, we don't technically need an equation. If we know they're both monoprotic, it's going to be a 1-to-1 mole ratio. But we will need this equation sooner or later, especially at the equivalence point, because we're curious what's formed. But you got your hydrobromic acid, potassium hydroxide, do your double displacement. You always get the water and the salt. Potassium's a +1, bromide's a -1, KBr. Potassium salts are always soluble, so it's aqueous. So there you go. So you can see the 1-to-1 mole ratio between these. That's a key factor in the neutralization stoichiometry we're going to be doing. It allows us to skip a few steps because these calculations are long and bulky. It's nice to have some shortcuts. So we're solving for the amount of the base. So start with your acid. Right? If you're solving for the acid, start with the base. So we have 15.50 milliliters of the hydrobromic acid solution. Let's use that concentration, 0.241 millimoles of the HBr solute per milliliters of the acid solution, so milliliters of solution cancels out. Boom. And we can see the 1-to-1 mole ratio, so 1 millimole of HBr reacts with 1 millimole of KOH, easy peasy, and that cancels that out. And then we have the concentration of the base, so there's 0.309 millimoles of KOH solute for every milliliter of KOH solution. Remember, concentration is solute over solution. Cancels out millimoles of solute, leaving us with the volume in milliliters. So you got to love that millimole per milliliter trick. 3 significant digits, 3, that's 4, that's 3, that's exact, that's 3. So that gives me 12.088 milliliters. Round that up to 12.1 milliliters of potassium hydroxide solution titrant. That's where the equivalence point happens. Now that we have our frame of reference, when we're going to draw our titration curve at the end, let's calculate the initial pH, a pre-equivalence pH, the equivalence point pH, and a post-equivalence point pH. If you're on top of it, part B, calculate the initial pH of the strong acid before you add any base. Go ahead and do that for me while I erase my board. How'd you do? This should bring you back a few chapters, right? I mean, this is stuff you learned way back in introductory chemistry, because we didn't really deal with weak acid, weak base equilibria until this semester. So this goes way back, strong acids. So we've got the strong acid, HBr. We haven't added the potassium hydroxide yet. 100% ionization for the strong acid. Don't really need the equation. You can do that in your head, but we know that that acid is donating its proton to water, ionizing to form hydronium ions and bromide ions. Since that goes to 100%, then the hydronium ion and the bromide ion, but we don't need that. The hydronium ion is equal to the concentration of HBr. And bromide is an anion from a strong acid, so that's a neutral ion. We don't have to worry about the bromide. So we know the concentration of the hydronium ion. Well, pH is just negative log of the hydronium ion. Yay! These are easy. So negative log of 0.241. And remember, the number of significant digits in a log term is the number of decimal places in your answer. So we have 3 significant digits, giving us 3 decimals. Also 3 sig figs. That's just a quinky dink, though. So take the negative log of 0.241. I get 0.61798. Good to 3 significant digits. Technically 3 decimal places. Oh, that rounds up to 0.618. So that's a strong acid for you right down there, probably below 2, somewhere around the 1 range. Very typical, right? Depends on the concentration and all that kind of stuff. That's our starting point. That's our first dot on our titration curve. So now in part C, let's take a pre-equivalence point. So anything before that volume. So what was it, like about 12 milliliters, 12.1 milliliters? So let's pick anything before that, probably something pretty close, 11 to 12 range. And let's go ahead and calculate what that pre-equivalence pH is. Let me give you your game plan here. So we're going to calculate the pH in a pre-equivalence region. Usually on an exam, I'll just tell you what the volume is. But since the equivalence point was about 12.1 milliliters, let's do it before that. So let's just say 11.00. Could have done 11.50, whatever. Let's do 11.00 milliliters of the potassium hydroxide added. So what I want you to do is do the stoichiometry. Right? Figure out the initial millimoles of acid you started with, figure out how many millimoles of base you added, and subtract them. The base runs out, and you'll have a leftover millimoles of acid. Divide that by the total volume. Remember, you added 2 different solutions, so you need to add the 2 volumes of the acid and the base together to get V total. And then that'll give you the concentration of the leftover strong acid. Right? 100% ionization, so H3O plus equals HBr. Negative log of that, you're good to go. So after you do the neutralization stoichiometry, it falls back to exactly what we did for the initial pH. Have at it, my friends. How's the beginning part going for you? Right, we got 11 milliliters of titrant added. So let's figure out how many millimoles of acid we're starting with. That stays the same all the way through the problem. And how many millimoles of base we're adding. This is how we do every neutralization stoichiometry for the pre-equivalence points and post-equivalence points. For any acid-base titration, doesn't matter. They're all the process is the same. So we had 15.50 milliliters of HBr solution to start with a concentration of 0.241 millimoles of HBr per milliliter. So to 3 significant digits, we have 3.7355 millimoles of HBr. That's our solute. Good to 3 significant digits. That's what we're starting with. The amount of base we're adding is 11.00 milliliters times its concentration, 0.309 millimoles of KOH per milliliter solution. Also restricted to 3 sig figs, gives us 3.3990 millimoles of base. Good to 3 sig figs. That's our limiting reactant, right? There's less base than there is acid. So when they neutralize in a 1-to-1 ratio, we can just simply subtract them, and what's left is the leftover HBr. All the base is gone, so we literally just have a solution of a strong acid left over. It's just less than we had initially. So to get the concentration of the leftover strong acid, take the millimoles of HBr left over after the neutralization, divided by the total volume of the two solutions. So the millimoles of HBr left over will be the starting amount, the initial amount, minus the millimoles of base you added. Because it's a 1-to-1 ratio, we can do a nice little shortcut there. So we'll take 3.7355 millimoles, good to 3 sig figs, minus 3.3990 millimoles, good to 3 sig figs. And we're going to divide that by the total volume, which is the volume of the acid, 15.50 milliliters, plus the volume of the titrant base added, 11.00 milliliters. Since these are additions and subtractions, we're limited by fewest decimal places. Really the largest absolute uncertainty, but we can go fewest decimals because they all have decimal places. So if we take the top, 3.7355 millimoles minus 3.3990 millimoles, we get 0.3365. Good to 2 decimal places, millimoles of HBr. That's the millimoles of HBr acid we have left over after neutralization by the added base when we're titrating. 15.50 milliliters plus 11.00 milliliters, both good to 2 decimal places, gives us 26.50 milliliters total. We're diluting it, right? So that'll give us a concentration good to 2 significant digits of 0.01269. 2 sig figs. That's the concentration of the HBr after the neutralization. Well, since HBr is a strong acid, that will also be the concentration of the H3O+. Take the negative log of that, get me the pH. Go ahead and do that. I got to pause and rewrite the board. I was so close to being able to do that on one board. Darn. All right, we know HBr is a strong acid, so the hydronium is the same as that, which would be 0.01269 molar, good to 2 significant figures. Let's take the negative log of that. We're right back into the last problem at the initial pH. It's just less of a strong base. So negative log of that, I got 2 significant digits there, so that gives me 2 decimal places in my answer. I get 1.8965. Rounds up to 1.90. So it's still, it was less than 1 to start with. So now it's 1.90. So it went up a little bit, but not much. Not much, because we still have leftover strong acid. Now we're going to see, we're really close to the equivalence point. So we've been kind of just barely going up, and now it's going to go boom. Let's calculate the pH at the equivalence point. That's one of the key points. So we've got the initial pH. We've got a pre-equivalence point pH. Let's do the equivalence point pH, and then we'll do a post-equivalence point pH. When you're on exams, you can skip all this junk. All right, I just want to prove to you why the pH is 7.00. Let's look at the neutralization reaction. Again, we've got the HBr plus KOH giving us liquid water plus potassium bromide salt. Anytime you're doing equivalence point, I don't care what titration, at the equivalence point you have water, because we're doing an acid plus a base, and a salt. We have to look at the cation and the anion of that salt and see if it has weak base or weak acid behavior. Now remember, cations that come from strong bases, sodium ion, potassium ion, those kinds of things, those are neutral, right? So strong, if you look at, remember that acid-base table, so the stronger the acid, the weaker its conjugate base, and vice versa. So the bromide is the anion from a strong base. So it's such a weak conjugate base, right? Acid conjugate base, that it's neutral. It doesn't hydrolyze or ionize in water. And the potassium comes from a strong base, so that's a super, super weak conjugate acid. So neither the potassium or bromide will interact with water. They don't have acidic or basic behavior, so they're neutral ions. So definitely review that video on the pH of ions. That's really going to help you here. But we don't have to worry about it for strong acids, strong bases. So the only species that contributes to hydronium ion concentration at this equivalence point is water. Remember, in the background, there's always water autoionization, which produces a concentration of 1.0 times 10 to the minus 7 molar, OH minus, and H3O plus. So if we take the negative log of that, depending how many significant figures you use here, I just use 2 sig figs. That would give us 2 decimal places, 7.00. And we're just approximating here, so 7.0 is fine, 7.0007 doesn't really matter. But we went from a 0.67 pH initially or so to like a 1 point something right before the equivalence point, and boom, all the way up to a pH 7. And that's where you just add like a drop or less in lab, and bam, that baby turns pink. Ha ha ha. So we've got the initial pH, pre-equivalence pH, equivalence point pH. We're moving up that steep cliff now. Let's do a post-equivalence pH right after the equivalence point. Ideally, we do one way over so we can get a real nice curve, like it kind of a mirror image of the initial pH. We'd have like a final one, but usually we don't have time. So let's do one right after that equivalence point, right around 13 mils or so. And that'll be our last one, and then we can draw our curve. Yay! Here's your official problem. We're calculating a post-equivalent point pH, and on a test, of course, I'd give you a volume. I wouldn't make you figure it out yourself. It's got to be after the equivalence point, which was 12.1 or something like that? 12.088, about 12.1. So anything past that's good. So let's take 13.00 milliliters, because we're probably getting a decimal point plate. Peanut butter. 2 decimal points from the Buret's absolute uncertainty. There we go. 13.00. So do exactly, this is neutralization stoichiometry, do exactly like you did in the pre-equivalence point. What's your initial millimoles of acid? Now, we already calculated that, so just transfer that number over. Calculate the millimoles of KOH that you added, and you're going to find there's more base than acid now because we're past the equivalence point. And it would be really pink at this point, like too pink. So calculate the leftover KOH millimoles divided by the total volume of the acid you started with plus the volume of the base you added, and that'll give you the concentration of the leftover KOH. It's a strong base, so that is 100% ionization. That'll be the concentration of your OH minus. Take the negative log of your OH minus, gives you POH, and a lot of people forget this last step. You want the pH, not the POH. So subtract the POH from 14.00, and you get the pH. And that's got to be bigger than 7, right? We have a leftover strong base, so it's probably going to be way higher than 7. Give it a shot. I almost got it all on my board again, but not quite. Oy. I need like a 10-foot long board. It wouldn't fit on the screen. Here we go. You don't need to rewrite the equation. I just like to see that. Of course, if you're not stuck on small boards like me, you have that with you all the time. So we see the 1-to-1 ratio. The initial millimoles of acid was 3.7355. That was from part C when we did the pre-equivalence point, right? So we always need to know what we started with. How much base are we adding? Well, I added 13.00 milliliters. We did 11.00 in the pre-equivalence one. Times the concentration, 0.309. It's exactly the same problem. Pre-equivalence and post-equivalence are identical. It's just flipped. In the pre-equivalence, you have leftover acid. Post-equivalence, you have leftover base. Hey! So I get 4.0170 millimoles of KOH added, good to 3 significant digits. Do you see that there's more base than there is acid? So the acid is the limiting reactant. That's why I put the LR there. We're going to run out of acid. That acid is gone. We've completely neutralized it. And now we're just adding extra base, which would be silly in lab because you don't want to go past the equivalence point. Anyway, but here we want a titration curve. So leftover strong base. We need to figure out the concentration of the leftover strong base in OH minus in order to get the pH. So let's do it. So the KOH concentration left over after titration neutralization. How many millimoles of KOH are left over after they neutralize each other, divided by the total volume of acid plus volume of base. All right, well, let's take the millimoles of KOH, 4.0170, minus the initial millimoles of acid, 3.7355. That difference, which is 0.2815 millimoles, KOH, that's how much is left over. Good to 2 decimal places, 2 decimal places. So we have 0.2815 millimoles of KOH left after the acid neutralizes a good chunk of it. Well, we started with 15.50 milliliters of the hydrobromic acid solution, and we added 13.00 milliliters of titrant base. So add those together, good to 2 decimal places, we get 28.50 milliliters total of solution. Let's divide those. We got 2 sig figs there and 4 there, so to 2 significant digits, we get 0.009877 molar potassium hydroxide. Finish it off for me. We know that's a strong base, so that will also be the concentration of the OH minus. Take the negative log of that to get the pOH and subtract it from 14.00. Boom, you've got your pH and your final data point. Go ahead and polish that off for me while I erase my board again. Once we polish this off, again, strong base, so we're assuming 100% ionization, so the OH minus should equal the KOH concentrations, which we calculated as 0.009877 molar. Good to 2 significant digits. Let's take the negative log of the OH minus to get us pOH. So negative log of 0.009877, 2 significant digits in the log term, gives us 2 decimal places, so 2.0053. Good to 2 decimal places. Now, this is a big mistake. A lot of people stop there thinking that's pH. It's not pH, it's pOH. Right? So now we know pH plus pOH is 14.00. So the pH will be 14.00 minus the pOH we solved for. So 14.00 minus 2.0053. 2 decimal places here, 2 decimal places there. You get 11.9470, which rounds up to 11.95. So it went from below 1 initially to just below 2 just before the equivalence point to 7 at the equivalence point. Boom! To 11.95, just 1 milliliter after the equivalence point, and then it just kind of drifts its way up from that point on. Let's draw a titration curve just to show you what beautiful mathematics we just did in a graphical form. Yay! Here's our very rudimentary pH titration curve. So I did my pH scale, in this case from 0 to 12. We didn't really go above 12. Ideally, I'd go to 14, but I ran out of room. And then the titrant volume, the KOH here, I went from 0 to 20. Usually I'll go to 25 or 50, but we didn't go much past that. The initial pH was less than 1. It was 0.6 something, right? I just took that value we had. I forget what it was. And I plotted that data point. There's my initial pH. The equivalence point was just over 12, which was at a 7. So see where the 7 is coming across? Right about 12 milliliters, give or take. We did one at 11 milliliters, and that was like a just below 1.9. So doesn't rise very much because you just got this leftover strong acid. So it just kind of stays low, and then boom! 1 or 2 drops right around the equivalence point, shoots up from like a 2 up to like a 10. Holy moly, look at that huge range. It just, bow! Like some cliff face. And then at 13 milliliters in the post-equivalence region, we were like 11.9 something, like 11.95 way up there. So anything below the equivalence point is the pre-equivalence region. That's your neutralization stoichiometry. Anything past the equivalence point is the post-equivalence region, neutralization stoichiometry. Leftover strong acid, leftover strong base, only water there. And we're going to find when we do weak species, this data point will shift above or below 7, and this range will shrink when we have weak acids and weak bases. So we could pick an indicator that falls between these lines. So you probably want an indicator that falls between those lines. So choose an indicator in this range where the 2 pH unit, right? The 2 pH range of the indicator falls somewhere between, maybe, just to be safe, maybe a 3 to 10 range or something like that. So if you got a lot of options here for strong acids. So if we're looking in the 3 to 10 pH range, right? So here's your 3. There's your 10. So any of these would work, right? This is why we use phenolphthalein, because it goes colorless to colored, even though it's off to the right, because we like colorless to colored. But you could have done any of these: thymol blue, phenol red, bromothymol blue. All of these you would have had. See, here you would have started like yellow to orange, light green to blue. So those would have been pretty cool to do. But all of those, there's probably 5 or 6 different indicators whose little pH range here falls between roughly 3 and 10. We'll find out we don't have as much leeway for weak acids, weak bases, so there's fewer indicators that would work. But you just look on that chart, make sure that little 2 pH range falls somewhere within that steep rise. There you go, strong acid, strong base. So the rest of these will be just like this with some subtle differences.